On the right side here, we're doing the same thing. Okay, a similar thing. But instead, we're driving a current, which
To
is
make the cool.
creating to drive the heat, the difference in temperature.
Agreed. To make
So
the thermal gradient.
right. So if I understand this correctly, if I have a heat source, if I have a delta T,
Mm-hmm.
then the electrons and holes pile up at the bottom, which
Mm-hmm.
creates a delta V,
Yep.
which can drive a current to
Yep.
heat to turn on a light bulb.
I like it.
But if I don't allow, if I allow everything, so
Or
if I
if
drive
I.
a current
Mm-hmm.
and I have a hot and a cold side,
Or you
then
maybe let's start with a thermal equilibrium,
okay, yeah, go
and
ahead.
then you attach it to a battery.
Mm-hmm.
So you push a current, you drive a current.
Drive a current,
You will generate a delta T,
and
a
then
delta temperature.
right, the delta temperature then creates a delta V, which then stops the electrons and holes from piling up. Is
I
that
guess
right?
that's true.
Because that's why they're not piling up in the right side.
I think they are also piling up. Although I see the picture looks even.
So I think okay. So we drive a current,
Mm-hmm.
which causes pileup, but then the pileup causes a delta T, which then
Okay.
offsets the pileup. But I keep driving current, and it wants
It's
to keep creating more of a delta T, but I keep siphoning the heat off, and that's my fridge.
right.
All right.
Yeah, exactly right. Right. So you'll find some equilibrium state if
Yeah.
you don't remove this heat to the outside world. You run
Right.
some water out of it or something.
See. So actually, the fact that they're evenly distributed is actually not necessarily the case. It just needs to find some equilibrium pileup condition. Is that right? If
Right.
I siphon more
So
heat,
if I put 3 volts in this battery, a
yeah,
little double A, right?
yeah,
Then I'll get some temperature differential. I don't know,
yeah,
5 Kelvin,
yeah,
arbitrary number. But if I put in 9 volts, so a much triple the current,
yeah,
then I'll get a temperature differential of, I don't know, 10 volts or whatever it is.
right,
10, not 10, 10 Kelvin.
yeah,
And it'll equilibrate. So if I want more cooling on the side, then I need to run some water or a fan over the hot side
yeah.
to extract the heat, and then this side can keep getting colder.
I like it. I guess I'm also worried about the even distribution of the holes and the electrons in the right picture, the Peltier effect picture.
Right.
That's not necessarily the case.
I
If
think
I
that
if I
is correct. I think you
I
would
if I
get some.
go ahead.
So I think you would get holes piling up. So each of them would have a distribution.
Yeah,
So it's not like this is only holes. This is only electrons.
yeah,
Let's look at just this end side. If the electrons are going this way, you'd pile up a bunch of electrons here. You'd pile up a bunch of holes here. Then you
yeah.
get this like recombination gap in the middle. Plus maybe some channel effects. Maybe like a pathway in the middle. I think.
Okay. So I was thinking if I supply a huge amount of current
Mm-hmm.
and I can't siphon heat off fast enough, then I
Okay.
get a certain type of pileup in the NMP materials.
Yep.
If I siphon too quickly the heat and I don't supply enough current, then I get a pileup in the opposite direction. If I supply just the
Yes.
right amount of current with just the right amount of heat siphon, then it'll be like in the picture. But the
Yeah.
equilibrium condition doesn't necessarily have to be no pileup. Is that right?
Ooh, I'm getting lost.
I'm really triggered by the fact that the holes in the electrons
Yeah.
on the right picture are evenly distributed,
Evenly distributed, right?
which
Well,
implies that
I'm also concerned that these are. What is this distribution? I would expect them a lot more pile up down here.
I see. I mean, I guess with these large number, like pileup in an electronic sense is actually a very few number, right? Because
Yeah.
it's like a huge number and just a tiny charge separation
Mm-hmm.
in materials creates a huge voltage.
Yep.
And so it's
I mean, it's an enormous number of electrons total,
right.
but it's like the percent difference from the equilibrium state is actually pretty small.
Actually pretty small, yeah. Okay, I think I'm okay. I don't have all
the
of
way
the
you said that.
I think I'm getting closer to sort of understanding this Peltier fridge.
Hmm.
I mean, in summary, you buy a Peltier fridge off of McMaster Car or from your favorite vendor, and then you hit the on button.
Yeah, and it works. Yeah.
And then it works.
You stack them up, you cool your computer. Oh, yeah.
Yeah, no problem. Actually, why isn't this used more often in computing? Is it not?
Oh, so I think the temperature differential per cooler per chip is not that much.
Oh, it's actually not that powerful.
Right. It doesn't make a huge temperature gradient.
I see.
What you can do is you can just layer them up, and then you can get a huge temperature gradient. But then now you're supplying power to each one of these, so it may not be worth it.
Right. It does have the nice advantage that it's kind of moving parts.
It's exactly solid state.
Yeah, so you don't need like some pump that's going to break, some fan that's going to get noisy.
Water, just dusty fan blades. Like, no, it's set and done.
So if we had like a hyper Peltier fridge that we could slap onto a CPU, that would be awesome.
That'd be super good. If I remember, this in combination with radioactive decays is how we power our long distance space probes.
Oh,
right.
Cool.
So you get something hot here, this radioactive pellet that's just warm because it's undergoing nuclear decays, which generates a hot side, which generates a voltage. No moving parts, no rotations, clever. no cadmium, lithium batteries.
Mm-hmm.
Like, just send this thing up.
I see. So it's actually the left side.
That's right.
Same.
So that's right. So heat source. This is the whatever fissile material that makes it hot, and then it generates power.
That's cool. I didn't know that.
The more you know.
The more you know. Okay. Man. Very cool. I wonder, okay, I don't think we do this now, but what is like, if we wanted an effective cooling rate for, say, a CPU in a regular gaming PC, what kind of Seebeck coefficient differences would be required? And is that even in the realm of possibility?
Is this like a meter tall stack of coolers?
Yeah. Or like if I wanted it to be like centimeters,
what temperature gains can I get?
What kind of, if I could make any Seebeck coefficient I wanted, what would the numbers be? Because that would go a long way. Man, that would really help. It would help gaming. That's what we're motivated by, is gaming.
Also be dope. I mean, scientifically.
Oh, it's gonna be doped.
So it looks like people still connected to a water radiator because you need to get the heat out of the system somehow.
But I guess if you're really, really clever, you could, because you have an integrated circuit, you could build the Peltier.
Piano. Okay, very nice.
You could build the Peltier refrigerator circuitry and
into the chip,
right into the chip. You wouldn't put it on the chip; it would just be built into it.
That's right.
Just like a parallel thing going on into the chip. That would be like cooling it from the inside out. That would be.
Gosh, yeah! You just etch it directly into the chip, just right at Intel. Just do it.
Right, and so then it's just another set of pins that you hook up that supply the needed current to run the Peltier fridge. And then you can hook up
you can't get better cooling than that. It's like localized exactly where you need it.
Right. And so that would be, that would probably be a way to get exceptional gains at the, the consumer level or just any level without actually doing much in terms of like nanometer sizes for new chips. That would go a long way. In summary.
Unrelated. I guess also related. It's super cool. So it's a thermoelectric fan.
Oh, cool.
So you have like a wood stove, and instead of pointing an electrical fan that you have to power and push the air around the room, you just set this thing on top. You get a little hot spot on the bottom. It runs up to the I guess Seebeck? Peltier?
It's gonna be Seebeck, right?
The same. So, I mean, it's the same thing, just depending
Reverse,
which direction we push the current, or if we use the heat source first. So I guess heat source.
Yeah.
And from the heat of the wood stove, it pushes the fan on its own.
Oh, that's cool.
So super good way to, if you have a wood stove, which are increasingly more illegal, if you have one, then you just set this on top and it distributes the air around the room, and instead of having a hot pocket right around your stove.
Okay.
Clever.
That's cool. That's super clever.
I wonder if you could scale this up to some type of geothermal wind generator, which you then convert from wind into electrical. Wait,
right. So
wait,
instead of instead of having a fan, you'd hook it up to some sort of what's it called?
If we already have the geothermal heat, that's already the hot side. We don't need to go through the fan. We don't need to go.
Right. Instead of having a fan, you'd hook it right up to what is it called? A dynamo?
Or we already have the voltage just generated directly. No moving parts. So this goes to your like steam vent and just gets, you put a metal, like a copper pipe there so that it gets hot, and then you pull the electrical energy just straight out of that.
I see. I don't think the Seebeck effect is used in geothermal, probably because it's not that good, I would guess.
Center of the Earth's pretty hot.
I guess what do? They do the steam thing in geothermal, where they like heat up some water, run a turbine. Instead of using the Seebeck effect, probably because the Seebeck effect is really weak.
6,000 K.
Okay, we've got to drill how far down?
To the center.
To the center.
Without melting the chips. In order to power our gaming rigs, we cool the center of the Earth.
Yep. Whatever it takes,
Magnetic field collapses. Okay, that's even better.
Yeah, no
All
interference.
The birds confused. Like a bird's like, I don't know where I'm going. Magnetic field's coming.
Yep.
TM. This is our idea.
Yeah, for sure.
Cool.
Okay, cool. Sure.
Good discussion.
That did not go where I expected it.
But we generated a marker track to mark the end.
Yeah.
Yeah, we generated a pretty cool discussion out of it.
Yeah.
And sitting in this zone of like, oh, I don't know. Like, actually, I took a class, like a electronics class.
Yeah.
By Dave Pellet back in the day. And we learned this stuff. It's been a long time.
Yeah, every time you revisit something, it's like, did I understand it before? I thought I did. Do you know this feeling?
I know, yeah.
Yeah. This happens so much. It's like, I'm like, I got it. And then I revisit a year later. I'm like, what? Did I understand it? What was I thinking?
But I explained it to someone else.
Yeah, like, what the hell?
Okay. Shall we shut down?
Let's shut down. 2025, January 2nd. This is SS Science, Nobel Prizes Physics.
2025, 0102. This is SS Science, recording for Nobel Prize in Physics. We only got to the second one.
Yep.
Okay. In 5, 4, 3, 2, and 1.
In 5, 4, 3, 2, and 1.
White cards.
Down. Oh, white cards.
Shut down. 104.